These are the notes on the Doppler shift. We already discussed the Big Bang, the earliest known event in the development of our universe. We also discussed what happened right after the Big Bang, and I do mean right after the period of inflation, the rapid expansion, and then, of course, the continued expansion of the universe since then. So basically, by rewinding this, it led astronomers to conclude the universe used to be smaller. So what was the evidence for the Big Bang having occurred? The two major pieces of evidence that we did discuss are the redshifts of galaxies and the cosmic background radiation. Now, the cosmic background radiation has a lot to it. I'm going to leave that aside for now, but we are going to get into exactly what does it mean when you say the redshift of galaxies supports the Big Bang and the expanding universe theories. Well, redshifts are just a type of a Doppler shift. So in order to understand about the development of the universe, the expansion of the universe, you kind of have to know something about Doppler shifts. The Doppler shift is the apparent change in frequency and wavelength of a wave from a source that is moving relative to the observer of the waves. So, if a source is moving toward you and sending out waves, what kind of waves? Well, they could be sound waves or they could be light waves, any kind of waves. If they're moving toward you and sending out waves, that changes the wavelength. If they're moving away from you and sending out waves, either sound or light, that changes the wavelength also. Or if you are moving toward the source of the waves or away from it, that also changes the wavelength. That's why it says relative to the observer. So either if it's moving or you're moving, or if both are moving, it changes the wavelength. You might be familiar with this if you've ever heard a loud noise. What's loud? Well, a fire truck is loud when its siren is on, or an ambulance when its siren is on. Something that makes a loud enough noise that you can hear it from far away. Well, if a fire truck is just parked there, not moving, turns out doesn't matter which direction you're in. If you're in front of it or behind it, you hear the same sound, the same wavelength. But if you're in front of a fire truck that is moving toward you, well, you don't hear the same sound. What you hear is a higher pitch sound. Higher pitches have a higher frequency, which means a shorter wavelength. The wavelength is actually compressed because every sound wave the fire truck sends out is sent from a different location, which is actually closer to you, which compresses. So try to picture the sound of this train, and let's say it blows its whistle and it's heading towards you. You sort of know what that would sound like, right? It's moving towards you and at a high velocity, and any loud noise it makes will be noticeably higher pitched, okay? It'll be a higher pitch because the object is moving towards you. So that's a good way to get off the tracks, get out of the way if a train is heading your way. On the other hand, if an object making noise, like an ambulance, is moving away from you, well, what you're going to hear is a lower pitch than what the object is actually emitting. Let's say if it was stationary, okay? Because every time it sends out the next wave, it is further away, sort of stretching the waves out, lowering the frequency, lowering the pitch. So in these three images, the top left, the middle, and the bottom right, we see waves being emitted from a source. In this case, let's call them sound waves. They're being sent out in all directions. So notice the one on the top left, because the sound waves are traveling out in all directions and the object is not moving, they're all evenly spaced. That does not have any Doppler shift. But for the object in the middle, well, it is moving to the right. So you can sort of see how each time it sends out the next wave, it's coming from a different position, which is closer to the wave on the right that it sent out previously and farther from the wave on the left that it sent out previously, which winds up compressing the wave fronts in the direction toward the right. So if you were on the right of that object, you would hear a higher pitch. And if you were on the left side of that object, you would hear a lower pitch because you'd be behind it. It would be moving away from you. The bottom right is a special example when the object is moving at the same speed as the wave. This can happen with sound because it is possible to travel at the speed of sound. We call that Mach 1. Mach 1, the speed of sound, about 760 miles per hour. If you move at that speed, then all the sound waves you're producing are traveling at the same speed you are. So you're keeping up with them in one direction. Then you make more sound, and it also remains with you, travels at the same speed you're traveling, and that eventually builds up to make a giant boom, what we call a sonic boom. So the object on the top left is a non-moving object. The object on the bottom right is moving at the speed of sound, producing the sonic boom. The same thing happens with light waves. But light waves, we don't hear, we see them, and the way that we see them is by their color. It turns out that every different color of light has a different wavelength. It just turns out that red waves are longer and blue waves are shorter. Violet waves are the shortest of the colors that we see, and everything in between in the color spectrum. So if the same thing happens with an object moving rapidly, sending out light waves, well then an object that is moving toward you is what we call blue shifted. It's shifted toward the violet end of the spectrum. For simplicity, they call it the blue end of the spectrum. And if something is moving away from you, well, it's shifted toward the red end of the spectrum. The wavelengths are made longer. They call that a redshift. So redshifts occur because the light waves are stretched out, because the object is moving away from you. The galaxies are moving apart from each other. So when Edwin Hubble noticed that pretty much every galaxy, almost every galaxy in the universe, was moving away from us, he realized the universe must be expanding. How was he sure they were moving away from us? By their redshift. And the galaxies that appeared to be close to us, usually they were bigger, they just happened to be closer to us, they weren't moving that fast, just a little bit. The galaxies that were far away from us were moving really fast. So the farther away the galaxy is, the faster it moves away, like in the raisin bread dough analogy. Even in the balloon analogy, that works. So whatever the wave started as, if it gets blue shifted, it becomes shorter. If it becomes red shifted, it becomes longer. Now, I'm not saying that colors are always turned to blue or red. They're just pushed in that direction. So we've already seen that there are many kinds of galaxies, many galaxies, hundreds of billions of galaxies out there. Remember that in this deep field view of the Hubble Space Telescope, there are so many galaxies, it's almost ridiculous. In this tiny little picture, all of those. And you might wonder, well, I wonder what it looks like in the brand new Webb Space Telescope, the JWST. How does that look? Well, let's see. there is a deep field view from the James Webb Space Telescope, the JWST. The way to tell it's a James Webb photo, by the way, is look at the lens flare around the bright star. See how that goes in 6 directions? Okay, that it's sort of hexagonal. That's because of the setup of the hexagonal mirrors. Also, these photos are taken in infrared light. They just make it look like it was taken in visible light. And you can see it's even more ridiculous because everything in this picture, except for the very brightest objects that have the lens flares, those are nearby stars, everything else is a galaxy. So there's so many galaxies out there. And you may notice that some of these are actually twisted and distorted. That is due to what we call gravitational lensing. So now we're getting an even better picture than we had before of how many galaxies there are out there in the universe. So when Edwin Hubble looked at many, many galaxies in the sky and measured their wavelengths of the light they were emitting, what he found was that almost all of them were redshifted. And the ones that were nearby that appeared bigger were less redshifted, meaning they weren't moving away from us as fast. And the ones that were farther away, that were really small most of the time, they were moving away super fast. So this is what led him to the conclusion that the universe was expanding. So if you saw a galaxy and its wavelengths were blue shifted, what would that mean? That would mean the opposite, that instead of moving away from you, it's moving toward you. Or you could say you're moving toward it, because it's all relative in space. No one is really standing still in space. There is a galaxy that is doing this. It turns out the Andromeda Galaxy is extremely blue shifted. In fact, the Andromeda Galaxy is going to collide with the Milky Way galaxy in about 4 billion years. That might sound like a long time, but actually that is before the end of the solar system. That is before the end of our sun's lifespan, when the Earth will probably still be around. So by the end of the Earth's existence, it probably will be in a combined galaxy of the Milky Way and the Andromeda Galaxy that will have collided and merged into what they're calling Milkdromeda. Not a great name, I know, but that's seriously what they are calling it. The only problem with this is that if you want to know how much a color has been shifted to the red, if it's moving away from you, you really have to know exactly what color it was to begin with. But we do. If you remember the spectral lines lab that you probably had in chemistry, I would love to do it again with you. And it's one of those things that it's really hard to do on a video. This is one of those labs I would consider doing if we came back and were in person at school. It's just a great lab, but you kind of have to do it in person. Well, if you remember the spectral lines lab, if you've done that one, then you know that every element has a very exact signature wavelength. Not just one, it has several signature wavelengths. So we know what those wavelengths are. And if we find one of those and we see how much it's been shifted, well, then we know exactly how much it's changed. Now remember, just because we call it a redshift does not mean that the colors are actually turned red. Notice that the second one down, the yellow wavelength, well, it still kind of remains yellow, maybe a little more orange now, but it's shifted toward the red end of the spectrum. That's what we mean. So the amount that the spectral lines are shifted toward the red is proportionate to the galaxy's distance away. So the farther a galaxy is away from us, the faster it's moving away from us, and the redder its light is shifted. If you remember the raisin bread dough analogy, or even the balloon analogy, then it kind of makes sense that this would work. So looking at all this information, Edwin Hubble was looking at these galaxies and measuring how much they'd been redshifted. He figured out the farther, the redder. He came up with the idea that the universe was expanding. Every bit of evidence since then has confirmed that. Now, I'm not trying to say that every galaxy is moving away from us, because that's not true. There are just a very, very few nearby galaxies that are not moving away from us. But if you get beyond a certain distance, every other galaxy, every distant galaxy is definitely moving away from us. And the farther they are, the faster they're moving away and the redder they are shifted. So now think about how that relates to the raisin bread dough analogy for the expansion of the universe. All of the raisins that are closer to each other are moving apart, but not as quickly as the raisins that have a greater distance between them. They're moving apart faster. This is exactly what we see with the expansion of the universe. Galaxies that have a greater distance between them already expand at a faster rate. So that's why this analogy is such a good example of the expansion of the universe. And once again, imagine the raisins inside the bread on the other side of the bread that you can't see, all of them spreading apart. But if they're closer together, the spreading will be slower than if they're farther apart on opposite ends of the bread. So that is the end of the notes on the Doppler shift. Thank you.